Hello everyone. Welcome to the yet another interesting one-shot review of AP Calculus. And this is purely BC topic. We are in Unit 9, Parametric Equation, Polar Coordinates, and Vector Value Function. Right. So as every video, I have covered the key concept and also the problem-solving techniques which is involved in these concepts. So I hope this video might be helpful to you. Let's get started. And so this is basically how we are going to apply the integration, the calculus stuff, and differentiation, these kind of things into the different scenarios, parametric equation, polar coordinates, and vector value. So three different forms. So it will be very interesting and stay tuned until the end of the video. So let's get started. First, defining and differentiating parametric equations. What is parametric equation? So equations where usually we will have y is equal to x square, something like this. But now x1, y are expressed in terms of a third variable. Usually we will use the t variable, the parameter. It depends upon the another parameter. X of t is t square minus 3, y of t is t plus 1 or sine t. So basically instead x and y, xy means it's Cartesian. But parametric means x and y will be expressed with another parameter, right? So this will represent a motion in plane. We can use it for modeling curves. And when x and y is directly not connected, we can get parametric forms. So x will behave in this way, y will behave in this way. Got it? So this is all about parametric equation. And differentiating stuffs is very simple. Let's go. So a simple example, you can just visualize how this parametric stuff will work out. A dolphin leaping out of water. So it will just come like this, right? Kind of a parabola shape. So the dolphin's forward motion increases as it moves through the air due to its momentum. So horizontal motion and also vertical motion. So horizontally it's moving and vertically also it's like a kind of wave structure is there. So we define horizontal with a particular equation and y is the vertical motion is something like this because the speed increase, the height increase and then it decrease. But horizontally, it's just go on and on, like not on and on, but it's just increasing. So in this case, it's better. It's a best thing you can just represent using parametric forms. Okay, so you can think, okay, dolphin do like this. It's a simple parabola, but this is the best one. You are separately defining horizontal and vertical motion. That gives the better idea than the simple y equal to x form of equations. Got it? Now, graphing parametric equations is very simple, the same x and y form. So create a table of values of t, which is the parameter. Sometimes theta will also be there. Compute corresponding x of t and y of t. Plot the points and connect them smoothly. It's very simple, but simple means the same Cartesian graph, but in terms of t, we have to work a little more. For example, if your x of t is cos t and y of t is sin t and you're going to plot it from 0 to 2 pi, you will get a unit circle, right? I hope you can recall the algebra stuff like how we define trigonometric function. So you will get a unit circle. Let me quickly explain this using the Desmos for you, right? And here we move. Yes. So here, this is a normal graph, x-axis, y-axis, and numbers are there. Now, you just define in your Desmos, like whatever. I take the simple cos t and sin t and give you a range 0 to 2 pi. So this will give you a unit circle. What if I do 0 to pi? It's kind of a semi-arc. And pi by 4, it's a quadrant arc. So something like this. And if you change that, the parametric form, like if I do t and here t square, let's do. So it's a kind of a part of a parabola rightwards. So if you do from 0 to 100, so it's a part of right? So if you do minus here and also minus here, so something. So changing the function will give the different results. Okay, this is simple, When you need a Desmos help, make sure the parametric forms in the parentheses include x and y stuff, and also make sure to give the bounds that you're working at. Okay, if I give 0 to 1, see, it's just a simple part. Okay, that's simple. And let's move into the part. So I hope this visualization might help you. And here we go. Now, differentiating parametric equation. Actually, we need dy by dx, but y and x are separately defined with variable t. So it's dy by, do you remember the chain rule? Dy by dt over dx by dt. So dt will get cancelled. Like you can express in this form. And that's simple. So the differentiate dy with respect to t and x with respect to t. Just divide them. You will get the dy by dx, the first derivative. Of course, we will see second derivative. Now, one more important concept, tangents to parametric curves. So tangent means tangent function is dy by dx function, right? And it is now we got, since it's parametric, it won't that simple. It will be dy by dt and dx by dt. For horizontal tangent, set your numerator to 0. Y with respect to t, that differentiation set to 0, and vertical tangent denominator 0. That's the simple condition you need to apply, right? Very simple. Differentiate, and you should know dy by dx is something like this, and horizontal tangent numerator 0, vertical tangent denominator 0, right? Now, second derivatives of parametric equation. Okay, so this is important. First derivative is this. Second derivative, you just do d by dx, right? But you see one thing, the denominator is remained untouched. Just you do the differentiation of d by dt into dy by dx. That will give you the second derivative. So you are differentiate, the denominator stays same, and d by dt, dy into dx is the, so we already calculated it, right? So that one. So don't put the same numerator, and just memorize this. Now, a simple example, a particle moves along a curve defined parametrically by x of t as t square plus 2t, y of t is ln t plus 1, and t greater than 0. We have many questions. Slope of the tangent line at t is 1. Concavity at t is 1. Equation of tangent line at t is 1. Intervals where the curve is concave up. So let's do one by one. First, the slope. Slope means what actually? dy by dx. But here, we have parametric form. So the rule is, first you differentiate x with respect to t. You got 2t plus 2. Basic power rule. And dy with respect to t, 1 by t plus 1. Now, dy by dx is numerator dy by dt divided by dx by dt, and plug in those values. Okay, just we are plugging in this. I hope you can follow. And simplify. We got 1 by t plus 1 the whole square. They will get combined, right? And that's it, my dy by dx. So if you substitute t is 1, that's it. The slope of the tangent is done. Dy by dx at t is equal to 1. And just plugging in stuff, we got 1 over 8. The slope of the tangent line to the curve is this in a parametric form, right? And determine the concavity of the curve. Do you remember concavity depends on second derivative? So you will find second derivative. We already have dy by dx, right? So let's take dx by dt and dy by dx. Now, d square y by dx square is, numerator is d by dt, dy by dx. Denominator stays as it is as the first derivative stuff. So make sure we are clear with this. And then you just start differentiating this part, which is d by dt of 1 by 2 t plus 1 the whole square. So when you manipulate, and here we can apply the chain rule. So minus 2, you applied the power rule, and then, okay, so you got this. Then you substitute, then you can just plug in over here into this. After simplifying, and dx by dt, you can plug in. So that's the next step. We are just replacing the known expressions. into the d square y by dx square stuff, right? And again, simplify. Now, we need the concavity at t is equal to 1, right? So d square y by dx square at t is equal to 1. We just want to evaluate it. And we got a negative. Negative means it's concave down at t is equal to 1. That's simple. Now, last one, sorry, not the last one, third part. Find the equation of the tangent line to the curve t is 1. Okay, tangent line, it's y minus y naught is the slope m into x minus x naught. Same concept. And here, in this case, m is dy by dx at t equal 1. This we have already calculated, right? So the slope we already know at 1 is 8. So same tangent line we are working at. So that work is easier for us. So we already did that. Now point on the curve t is equal to 1. So just plug in what is x and what is y. It's very simple. X, when you plug in x is 1 here, 1 square plus 2 and simplify, and y in this stuff, you got this. That's it already. You have a 2 point and 1 slope. Sorry, 1 point and 1 slope. So which is 3 comma ln 2. And slope is this. So y equal to 1 by 8x plus b. To find b, use this point 3 comma ln 2. Okay. I just plug in y value and this will give you a b. So y equal to 1 by 8x plus b can be replaced with this. This is the equation of the tangent line to the curve at t equal 1. So similarly, we can do for any points. Next, identify the intervals where the curve is concave up. So concavity, second derivative, we already had the second derivative. So up means it should be always greater than 0. But as we found, minus 1 by 2, this will always greater than 0. 2 is positive, 1 is positive, t plus 1 will be always greater than 0. But I got something. I need a positive, but this will be every time negative. So this is actually less than 0. So there is no concave up thing in the entire curve. Okay. So you can even use sign diagram, but it clearly states. So sign diagram means you plot the negative, like the critical point, and check the sign. Throughout you will get minus. So which means the concave or the curve is never concave up. It's always concave down. And now, finding next part. So that is simple. The first two part, basic definition of parametric stuff and how to differentiate it and how to twice differentiate it. Now finding arc length of the curve given by parametric equations. Okay, so let's get into this. So formula for arc length in parametric form is integration. Integral a to b. Square root of dx by dt square plus dy by dt square times dt. This is the length and it's very simple. You know x and y in form of t, differentiate them and square it. It's not double differentiation. Differentiates. First differentiation whole square. And a to b means from which point to which point we need the arc length. That bounds should be there. Very simple. And a simple example. A particle moves along a curve defined parametrically and the stuff is given. They give the bounds. Find the arc length of the curve for t is equal to 0 to 2. So first thing, right, you know the formula. Dx by dt and dy by dt you can separately found. This is all we need. And bounds is directly given. So length of parametric curve is this, and you just write it. Now replace everything, the bounds and dx by dt, and simplify it. Okay. And yeah, sometimes here, it's not always simple integration. We have to do some manipulation techniques. So I have take 6t square common, like 36t square common. So when it comes out of square root of 36 is 6. Square root of t square is t, and remaining will be 1 plus t square dt. Now, next, to integrate this part. So u substitution will work. Take u is equal to 1 plus t square, and when you differentiate, du is 2t dt. So t dt can be replaced with half du. Okay, so now, also you have work on bound. When t is 0, what is u? Because we are shifting everything into u. When t is 2, what is u? That's it. So now replace everything into U form. L is 6 by 2. Bounds also you need to change. So root U du, right? And then now it's a simple stuff, U power half power rule of integration. So 3 integral 1 to 5 this, and U power half plus 1, which is 3 by 2 by 3 by 2 and 1 to 5. Now upper bound minus lower bound, you need to substitute it and do all the simplification is very simple. So I'm just doing that, going very fast here. So this is simpler form, right? So the arc length is 2 5 root 5 minus 1 units. That's simple it is. Now 9.4, defining and differentiating vector valued functions. Okay, so this vector valued function is mostly we will to understand the particle's motion. So far we did like horizontal, vertical, like a 2D motion. But what if it is in 3D? It's direction based. So it's important to understand how to define and differentiate vector valued function. Let's get started. So what is vector valued functions and how it will look like? So R of t is 2D vector is x of t. It's very similar to parametric, but the notation changes. Parametric will not tell us the directions, but this will tell the direction and also magnitude. And 3D vector will be also there. So R dash of t is just differentiate the components individually, nothing else, right? And 3D vector, it's also same. Individual components you need to differentiate, right? So now R dash of t will give velocity of a particle. This is position vector we will say. Usually what we will say, the original like normal y equal f of x, like s of t is position, like first function. So this is here we will call position vector. You will be having directions also. And when you differentiate, it will give velocity of a particle at time t. And so norm r dash of t, it's looking like a modulus, but in vector, we will use the double modulus symbol, which we call this norm of a vector, which is a speed. Actually, to represent magnitude, the speed of the particle, and how to calculate speed means it's a number, right? So norm r dash of t is square root of x dash of t square, y dash of t square. And if it's a z, you can just extend the formula to plus z dash of t the whole square. It's very similar to modulus form, but we have some difference in notations here, right? And this will give speed, r dash of t will give the velocity. Now, a particle moves in a plane according to the vector valued function. They defined it. Find velocity vector, determine the speed, find acceleration, compute the total distance traveled by the particle. Let's solve it one by one. Velocity vector, just differentiate individual component. 3t square becomes 6t. Differentiating and ln t plus 1, 1 by t plus 1. That's simple. Now speed of the particle, norm. We know the formula, right? I hope you will remember. Individual components into square and sum it. And we got, this is r dash of t. So square root of 6t the whole square plus 1 by t plus 1 whole square, and you can simplify it, right? And you can simplify, otherwise you can directly plug in, because I need the speed of the particle at t is 1, so you can directly plug in, replace t with 1. So r dash of 1 is this. Simplified further, these are simple simplifications. So I got root 145 over 2. That's the speed. And now, acceleration, it's very simple. You already got r dash of t. Again, r dash of t if you differentiate r double dash. So individual component differentiation, nothing new. So this is r dash of t, r double dash. 6t when you differentiate, it's 6. 1 by t plus 1 if you differentiate, minus 1 by t plus 1 the whole square. Now, compute the total distance traveled by the particle from 0 to 1. So total distance means the distance will be 0 to 2. It's always depends on the rate of change of the function, right? So we have to use the rate change, and this is the formula. Okay, so for the compound, so it's a to b modulus of the rate change, like norm for vectors, we will say r dash of t dt. So that's it. Now you know r dash of t. So it's not r of t. That is the only thing we have to calculate. This we already know, and we need to differentiate it. integrated. So simplify, but it seems complicated. Yeah, we have, in this case, we can use the Desmos and the calculator stuff. So let's do this with calculator. Okay, so we simplified as much as possible, but here itself we can go with calculator. So very simple. How we can do with Desmos? Let me demonstrate this for you. Here we go. So first thing, take a blank graph and give your f of x. Whichever is your integrand, you have to give that. So 36, actually there is t, but here you just make it as x. It will add some slider and stuff. And 36x square plus 1 by x plus 1, and you just give the integration and bounds. So integration, how you will give is int and your bounds 0, then go up and 2. So whatever you define f of x, you just plainly give that. So that will evaluate the integral. So there are complex forms, but if it's a calculator paper, yes, you can do this. Okay, very simple thing. Now, moving into the lesson. Right. Now, 9.5, integrating vector valued function. Yes. So we just did integrating stuff. It's very similar to that. So R of t is x of t, y of t, z of t. It's a 3D vector. And integrating means every individual component you need to do that. Okay. Now, if r dash of t is a velocity vector, then integral r dash of t gives the position vector. So going back. So it's very similar. Do you remember we connected position, velocity, and acceleration? Same with vector value. Just it was giving us direction. That's the only thing. And denotation is slightly different. So if r dash of t is a velocity vector, then integrating that give you position. If r double dash is your what we call acceleration vector, integrating will give velocity. Very similar, right? A particle moves. Wait a moment. Yeah, so here is a question. A particle moves in the plane with velocity vector v of t is 3t square comma e power t and 0 to 1. The particle start at 2 comma 1 when t is 0. Find the position vector and determine the position of the particle at t is 1. Find the position vector r of t. Okay, so it's r of t, not r dash. You know that, right? Okay, now, first position vector, integrating v of t. V of t is r dash of t. Integrating r dash will give you r of t. How will you? You will just integrate each component. And here it's simple example I have taken. So when you're going back, integration. So it's 3tq. And make sure you're giving the constant of integration, don't forget. Right? And C1 and here C2. Now, this is not like, it's a family of solution. I need a particular solution so that they give some clue. The particle starts at position 2 comma 1 when t is 0. So this is 2, this is 1 when t is 0. So let's solve this. Apply initial conditions to evaluate the constants of integration. And when t is 0, the particle is at 2 comma 1. So tq plus c1 is 2. So just equate it. And when t is 0, this is what? So 0q plus c1 is 2 and c1 is 2. Same thing here. E power 0 plus c2 equal 1. Right? So when you solve this, you got the constants. Now r of t becomes complete. tq plus 2 e power t. Okay, wait. E power 0 is 1 and 1. Yeah, right. So this is a position vector. And determine the position of the particle at t is 1. You know, like position vector now. So just plugging in t is equal to 1. That's very simple. And position means again it will be a vector form. So 3 comma e is the position of the particle at t is 1. So right. Now 9.6, solving motion problems using parametric and vector valued function. Motion problem means like position, velocity, acceleration, right? So these problems, let me recall you the concept. We did this multiple times, but yeah, it's that much important it is. So what is basically motion problem? We will analyze the movement of the particle in a plane or a space when it comes to vectors. Yeah. And displacement, the net change in position, and distance travel, the total length of the path. Velocity and speed, the rate of change of position is velocity, and speed is the magnitude. Acceleration, the rate of change of velocity. Only the denotation will slightly differ, like instead, like in parametric and vector valued form. So in parametric or vector value, position, velocity, and acceleration, we will usually go with this, and vector will have this kind of stuff. But in parametric, we'll just have x of t, y of t, like this. Okay. And now key formulas. Displacement is if you know the position r of b minus r of a. So like you need a displacement from a to b. So position vector, you have to plug in. Like I did r bold, which means r vector. Okay. Total distance travel depends on integration from the bounds you have to give and the magnitude of the speed, we can say. Right? And always here rate of change of the position. Now speed is that we know. Velocity and acceleration. For velocity, differentiate position, and for acceleration, differentiate the velocity. The same stuff with different notations. Now, a particle moves with position vector, this. Okay, so t square minus t. What is the speed of the particle at t is 1? Speed is norm r dash of t, like I mean the vector. So find r dash of t is very simple. I think I can just show you what is happening, what we have to do here. R dash of t, you have to just differentiate them individually, like each component. We did that. And speed means magnitude, which is norm of r dash of t, and that formula will go square root of the component square. So 1 by t plus 1 whole square plus this. But at 1 they are asking, so just plug in 1 and simplify. You will get some answer in the options and you will get root 5 by 2. Okay, that's simple. Now, we are into new form, which is polar form, defining polar coordinates and differentiating in polar form. Polar form is something which deals with radius and theta. Like so far we did something x-axis, y-axis. Now we will do everything in angle form. Like this is more like it will have an aesthetic sense in its graph form. It will be very interesting also. So let's get into this. Polar coordinates represent points in the plane using distance from origin and the angle. For example, how I will mention a particular point means, okay, this is 5 meters and it's making 20 degrees. So this is how I will refer a point in polar form. Radial distance and angle. And this is different from Cartesian coordinate. Of course, we will use x comma y, but in the normal form. But here, it will be something radial distance and the angle. An angle is always between from positive x-axis. So when you want to locate a point here, like 10 units and this angle you have to mention. Got it? Now, conversion between polar, but sometimes we need to understand in Cartesian form. So if you want to convert from polar to Cartesian, x is equal to r cos theta, right? And y is r sin theta. From Cartesian to polar, so polar means I need r. How can I find r? Square root of x square plus y square. How can I find theta? Tan inverse y by x. These x and y will be known for us. So you can note this simple formulas. Now, when a curve is defined in polar form, r is equal to f of theta. But its Cartesian coordinates will be fixed. X is r cos theta, like y is some r sin theta. Now, what is dx by, of course, do you remember we did in parametric form? Dx by dt, dy by dt. Here it's theta. R is just a number. Theta is the one which will be changing. So dx by d theta is, apply the uv rule. First you differentiate u, dr by d theta, v as it is, plus when you differentiate, like r will be as it is and cos theta will go minus sin theta. Similarly, differentiate y with respect to theta, you got this. dy by dx is very similar to parametric. Instead t, we have theta. dy by d theta by dx by d theta. And that's simple. Now, a simple question. The curve is given in polar form. Find dy by dx in terms of theta. Find the slope of the tangent line. Verify if the curve has a vertical tangent. These things we already know. Like how parametric we dealt with, it's very similar. Find dy by dx. Okay, what is x here? X is or cos theta and or is given to us. Let me show it here. Right? So x is r cos theta. These are fixed forms. Instead r, you just replace whatever they define. 2 plus cos theta. And how this cos theta comes? Because x is r cos theta. Okay, you just replaced r and this is default cos theta. And y is r sin theta. We have to do the same. Now we differentiate this uv method. This is your u, this is your v. And I'm not repeating. This is very simple. So we are differentiating x with respect to theta and we are simplifying it as much as possible. So I simplified a lot. But if you find it's kind of not that much needed, you can just stop here, right? Now, so here we have, I have just applied minus 2 sine theta, like sine to theta, double angle formula I have applied. If you don't know, that's fine. You can just simplify until this or until this. Now, okay, only one part is done. Same you have to do for y. Y is r sine theta. So r is 2 plus cos theta and sine theta. They are in product. So uv method again and apply that and simplify. So here I did some simplification, but still you can stop here or here or here. Now dy by dx is, you have dx and this, write the formula like, and then try to write like this. So this is your dy by dx. And yeah, this will always help us in slope, tangent line questions. So it's very important. Find the slope of the tangent line. I know the slope form. Just now we did. And just plug in pi by 3 over there. So cos 2 pi by 3, 2 cos pi by 3. So everywhere in theta, replace with pi by 3 and simplify it. Right? So cos 2 pi by 3 is minus half, pi by 3 is plus half. Sin pi by 3, root 3 over 2, 2 pi by 3, it's minus root 3 over, again root 3 over 2. And you simplify for this, you will get the slope. So minus 1 by 3 root 3. When you simplify again, like here I did root 3 over root 3. So in case of MCQs, we have to cope up with the options. So just practice the utmost simplification, which will be really helpful to us. Okay, we will get stuck and we will be searching for that option. And right, so try to always do the utmost simplification. And now, verify if the curve has a vertical tangent. If it doesn't have a vertical tangent, dx by d theta will be 0. In parametric form, we did this. I hope you remember. So take your dx by d theta equals 0 and at pi by 2. So write your expression for dx by d theta and plug in pi by 2 in terms of theta. If it becomes 0, yes, vertical tangent. Otherwise, no at that particular point. I think no, we don't have. Okay, we just plugged in. It's not equal 0, so no vertical tangent at pi by 2. That's simple. Now 9.8. Find the area of a polar region or the area bounded by a single polar curve. Okay. So this is the formula. Area of a polar region from r equal to f of theta from particular bounds. It's very simple. Half a to b. So don't forget it. A to b r of theta the whole square d theta. Okay. Now, you have to sketch the curve. Here it's very important to understand a little change might cause a complete different area. So sketching a rough curve is important so that we are very sure that we are calculating the correct region. Identify the bounds. Sometimes bounds will be given, sometimes the intersection when we are dealing with two curves. Now set up the integral. If it's a one polar curve and the simple integral and solve that. like you can use Desmos or some methods, substitution parts, many methods we have learned that you can do. And interpret the result. So it should give you positive area. Sometimes it will give negative. So recheck. We might have did some mistakes in finding, like interpreting the bounds, right? So make sure to do that. Now, find the area of a region enclosed by the polar curve, 2 plus 2 sine theta. Okay, how that will look like? How can I sketch this? Right? You can use Desmos here, and let's go. Okay, let me share this with you. Here you can see. So there is a curve given to us. Only this curve, they didn't give any bounds and all. But let me show you how to do this. Here we go. Right. So first r is equal to, we'll just give your r of theta. Don't give r of theta, just give r. And you know the integration formula, just give that. And a to b, you can just give the bounds, right? So 2 plus 2 sine theta is a kind of a chordoid, we will say this particular shape. And yeah, so you can turn into polar form for a better thing. So yeah, this is how the polar form will look. Not like a normal x and y, but like, can you see the difference? It's based on angles. So we didn't divide it into squares, like not unit squares here, right? So that's simple. You can visualize from it, from this kind of an apple structure, right? And now I will help you with analytical form. That's more important. And here we go. Okay, analytical form. We know the formula for a single polar curve, and we have to do it. They didn't mention it, right? Like from which to which. So 0 to 2 pi is one complete stuff. So you can do that. 0 to 2 pi, 2 plus 2 sine theta whole square d theta. And express this integrand, like expanded, 4 plus 4 sine square theta plus 8 sine theta d theta. And apply for, like, their integrands are in addition, so you apply the integration for each term. That's the next step. So half 0 to pi 4 d theta, half 0 to pi 4 sine squared d theta. And try to simplify the numbers. If any simplification possible, do it by here itself. So first term, area of part 1, I take 4 outside, and d theta when you integrate is just d theta and 0 to 2 pi. So you will get outside 2 and 2 pi minus 0, which is 4 pi. Then second area, we will calculate here. It's actually 1 over 2, 4 sine square theta d theta. Take 4 out. 4 by 2 you will get. And I write sine square theta because it have a power. Trigonometric power, we don't have anything. So try to make without power. Sine square theta can be written as 1 minus cos 2 theta by 2. And you can now, this is splitting into two terms, 1 by 2 minus 1 by 2 cos 2 theta. So that first 1 by 2 is 2, 1 by 2 d theta. And then minus 2 cos 2 theta, like actually it will be 4, right? So this 4 and this 1 by 2 becomes 2. This is 1 by 2 and d theta. Then again 4 and 1 by 2 becomes 2. And this cos 2 theta will be there. Right. And next we can just apply this theta, and yeah, half and this will get cancelled. This will be theta minus 2. Cos 2 theta, if you integrate, it will be sine 2 theta by 2. Right. And then, yeah, here one more half will be there, actually. So 4 by 2, it's 2. Yeah, cos 2 theta by 2 will be there. So this will be ignored. So sine 2 theta by 2, 0 to 2 pi. And just simplify and plug in those. So sine 4 pi and by 2 will be there. Anyways, pi will be 0. So A2 will be just 2 pi. Okay. Now, A3, the third term we have, it's 8 sine theta d theta. And sine theta, so it's very simple. Take 8 out. 8 by 2 is 4. Sine theta integration is cos. And it's a negative cos. Right? So 0 to 2 pi. So 4 cos, negative cos 2 pi minus of plus cos 0. So we'll get, anyways, like cos 2 pi, it's 1. And cos 0 is also like 1. And this will become 0. So totally we got 6 pi square units here. Right? So this is a basic integrations we have did here. Now, so here there will be a plus, minus of minus. So it should be minus 1 plus 0. Anyways, it's 0. And one more thing, sine theta, like we are integrating sine theta and whatever number that integral 0 to 1 complete revolution, and sine, when you integrate, the area will be 0. You know why? You don't want to even do this much. It will be 0 for sure because sine theta will look like this, 0 to 2 pi, and they are symmetrical. So whatever region here, the same region will cover. One is positive, other is negative, so they will become 0. Okay. Now that's it. We have added every term, and 6 pi square units is the answer for this. This is the polar region, finding area of a polar curve. Right. Next, what if it is the region is defined by two polar curves? Let's see. If the region is defined by outer curve or outer theta and inner curve or inner theta, area is this. It's very similar. Half and that r theta square, right? But here r outer minus r inner. Outer means which have a larger radius, inner means which have a smaller radius. And AB is a bound. Here, the intersection points. It's not 0 to 2 pi every time. The curves will intersect at some point. Like, for example, this is my curve and this is another curve where they are intersecting. And also, finding bounds is very important here. A little confusion might arise, might give a different area. Okay. Now, find the area of the region inside a polar curve. R is equal to 3 plus 2 sine theta. But outside the polar curve, R is 2. So they mentioned something inside this, but outside this curve. Okay. So inside means what? If this is like, imagine a circle. Inside a circle means like less than that radius. Outside means greater than. So the same thing, inside means R less than 3 plus 2 sine theta and R greater than 2. And we should identify which is outer and which is inner. So this is how the thing will be there. So this cardioid, 3 plus 2 sine theta and R is 2. So this shaded region, it's inside the cardioid, but outside the circle. Okay. Now this is the intersection points. We need to find it. From graph, like from Desmos, it's very easy, but analytically how to solve this? Let's see. So first intersection points, equate both of the curves. 3 plus 2 sine theta is 2. Sine theta is minus half, like 2 minus 3 is minus 1. And when you solve for it, one complete revolution, 7 pi by 6 to 11 pi by 6. Okay. So let me do one thing. 7 pi by 6 to 11 pi by 6 means here is 7 pi by 6. Here is 11 pi by 6. If you take that as a bound, this is the region they are meaning. Okay. This bound says, okay, 7 pi by 6 to 11 pi by 6. What is the area? This is the area, but I don't want this. So bound is very important. This 11 pi by 6 can also be mentioned as minus pi by 6, right? So you are taking from this to this in a clockwise direction. So the bound is 7 pi by 6 and lower bound is minus pi by 6. So in that case, it means, okay, the defined region will be exactly what they will be asking for, right? And that's how it's important. So when you just do it algebraically, you will end up with this, but this might give us a wrong answer. So always check the bounds. but theta is minus pi by 6. The reason is minus pi by 6 to 7 pi by 6. Right now. So area is, we have the bounds, we have the expression from the graph, it's clear. This is the chordioid is outer curve, this is inner curve. And we need to square that. Then simplify the integrand form, like expand it and try to simplify. This is as much simplification and apply the integrations for every part. So 4 and 1 by 2, 4 by 2, sine square, then 12 by 2 sine, then this. And we are going to evaluate each term separately. Okay, so it's 2 and after simplifying. Now, first area, 2 minus pi by 6 to 7 pi by 6 sine square. And yeah, we don't know this sine square form, so 1 minus cos 2 theta is what we're going to do. I expressed this differently, then I am applying integration to each stuff and basic integration here. And we got this as an answer. So make sure you're doing it properly. So this is first part. Now second part. 6 sine theta. It's very simple one. So sine theta is negative cos and you apply the rules, apply the limits, and you got something like this, which is 6 root 3 square units. Now, third area is this 5 by 2 d theta. It's simplest ever, I will say. So this gives us 10 pi by 3 square units. Now we're going to combine everything and you get 14 pi by 3 plus 11 root 3 by 2 square units. So using Desmos, let me give you a quick thing. So this is my first curve, or less than 3 plus 2 sine theta and or greater than, and we are solving for 0 to 2 pi. So we got this gray shaded region. That's what we need to work out. And if you just give 11 pi by 6 to 7, it will completely give different answer. My negative 2 points. So it's not correct because it's below the x-axis. That's the reason. So it's negative pi by 6 to 7 pi by 6. That will give you around 24.18. The same thing we got in an algebraic approach. Right. Now, that's it. We covered everything. We are into the key takeaways. Differentiating parametric equation is very simple. X will be defined separately. Y will be. So, first differentiation is dy by dt over dx by dt. Second differentiation, the denominator will stay as it is, but the numerator will be d by dt of dy by dx. Arc length of parametric curves, a to b, dx by dt whole square plus dy by dt under the square root. Then, vector valued function, just differentiate and integrate the individual components. Nothing different. And we will apply this for motion related problems. And this is also important, the norm of r dash of t, which will give you the speed. Now, differentiating in polar form, the standard x and y form of polar form is r cos theta or sine theta. So dy by dx is this. And area enclosed by a polar curve, single curve is half r square theta integration. Not r square, r of theta the whole square. By two polar curves, it's outer minus inner. And also, yes, square will be there, d theta. And here we should be careful with the bounds. This is the important part, right? And that simple it is. So we have explored calculus stuff like basically integration and differentiation with three different forms: parametric, polar, and vectors. So vectors gives us a direction, parametrics maps the journey, and polar curves adds the artistry. Yes, so it will be very interesting when you use the Desmos and understand it better. I hope this video might be helpful to you. If yes, you can show your support by sharing and giving us a like. And that's it for this video. I will be meeting you with the final one-shot review, which is Unit 10. So stay tuned and you can just comment whatever you feel about this video. Until then, keep learning, keep watching. Thank you for learning with us.